Uh, I begin by thanking the organizers for having this annual StatFizz meeting. The title of my talk is Self-Assembly of Linear Polymer Chains Using Spherically Symmetric Potentials. So let me begin by what is the aim of the model. So I want to come up with a potential spherically symmetric, no angle dependent, so that particles interacting via that potential form linear polymer chains. So that could be examples of equilibrium or living polymers, because particles interacting via the potential will self-assemble. They can break and join. And the point is, I want chains, linear polymeric chains, semi-flexible chains, but I don't want to use any angle-dependent potential. So I want radially symmetric potentials, and I don't want any branches. So this problem was actually suggested to me by Rahul Pandit right at the beginning of my PhD. So the origin of the problem goes back to 1997. And the key idea that Rahul wanted me to implement at that point was have a Lennard-Jones potential, so that particles interacting via that potential like to cluster together, but add a suitable term, whatever term be it, so that there's a potential maximum here at around a distance of root 2a or root 3a, a being the distance between two particles, the diameter of closest approach between two particles. And I tried out with a Lennard-Jones interaction, which will give me a minima, and I tried to add a exponential potential that I try to get a peak. But however much I tried, I could never get a huge peak which will keep particles away and form a long chain. If I added, increase the value of this so that I try to get a potential maxima at some distance here, which will stop particles from clustering and form a polymeric chain, then this potential minima would get destroyed. So I could never do it for many years. So the larger scheme of this problem is also, I mean, people work with patchy colloids, directed interactions, and so on and so forth. But the general scheme is how to obtain directed interaction, starting out with spherically symmetric potentials. And Geisler from Berkeley has been trying that using a large combination of particles, spherically symmetric interactions. Some are attractive, some are repulsive, they are different sizes. And there has been a nice review article in ACS Nano in 2014. Okay, but I'm not trying different structures, I just want a simple linear polymer chain. And after many years of trying, I managed to figure out what was going wrong. If I replace my Lennard-Jones potential r to the power 12 minus r to the power 6 by instead 2412, so that I have a much sharper potential rise at very short distances. So the repulsion at short distances, at a distance of sigma, rises very fast. And then I add an exponential term by r, which is reminiscent of a screen-Coulomb interaction. Then I'm able to nicely get a potential minima at short distances, so particles will cluster. And I have a peak at an appropriate distance, so that particles coming at a distance, I mean, approaching particles on the side of a chain would get repulsed. Okay, so I did manage to get polymeric chains, but they had branches. So I could never still fully solve it at this point. But at least I got my minima and the maxima in a way by using these little changes. Yeah. Zubutov potential. Did he get polymeric chains? Even with this, you don't get polymeric chains. I was not aware of it. So I have just added this. Yeah, I was not aware of it. But okay. But even with this, I got polymeric chains with branches till I introduced two kinds of particles, A and B. Okay. So now with one kind of particle, I always get polymeric chains, but a lot of branches, which is reminiscent of clustering. But if I have two kinds of particles, A and B, A and B have the same potential as I explained in the last slide, but AA and BB basically have purely repulsive interaction. So what happens, then they would get linear polymeric chain without branches. So the idea is, suppose this is A and this is B, because of this potential minima, they will get attracted, yes, but when, and then this is B and A, again they would form attraction by this potential. But if another A particle, or B particle tries to approach from this side and form a branch, then this potential has been tuned to the right distance, is exponential kappa by r10, and that will repulse it away. This prevents branching. So I'm finally able to get, with two kinds of particles, it's still, the potential still remains radially spherically symmetric. I'm able to get my linear polymer chains without branches. And this is the thing which worked. And suppose this was ABA, I keep the distance of A and B particles fixed at 1.2 sigma, then the potential seen by a combination of B and A, which is along this linear chain, it looks something like this, where I basically added this and this. So there still remains the potential minima, there remains a potential hump, and I get a linear polymer chain. These are snapshots, Monte Carlo snapshots from my simulations at relatively low number densities. They have self-assembled, there are many monomers, there are small chains. You increase the density slightly, the length of the chain slightly increases. This is not, of course, discernible from these snapshots. So what you do is basically calculate the number of chains that you get with different lengths. Lengths in this case, in one chain, how many monomers there are. And if it's supposed to model a living polymer, self-assembled equilibrium polymer, you're supposed to get exponential in a semi-log plot at different densities, which I do get. And then this is the length versus the number density. So the length slowly increases, average, as you increase the density, and at a certain density, the sudden jump. Okay, so this data has been basically shown again. The average length increases, and here there's a sudden jump. And basically for equilibrium polymers, it is known by Cates and Kandau that the average length should go as volume fraction to the power half, or number density to the power half. And this is what I get within this range. And of course here there is this jump, and this jump corresponds to a hexagonally ordered phase. So as you increase the density, what I get is basically all the chains get perfectly ordered into a hexagonal structure. This is the top view, you see this is surrounded by 6 neighbors, this is the side view. Of course, if you increase density further, then you do get branches, because there's nowhere that the particles can go, and they form a gel phase. But I'm not really interested, for my future studies, I'm not really interested in the gel phase at the moment. This disordered state to this hexagonal state is the first order transition. I can calculate the potential energy versus the number density, and at this density there is a jump. This is the total potential, the red one is the total potential energy. This is the first order transition. Number of branches become very low even as you go to higher densities. Of course, I'm not interested in the gel phase. Here it goes from 10 to the minus 6 and increases to 10 to the minus 2, but I still, that's per snapshot. So I do have a very low number of branches, which had been one of my original aims. Can I tune the persistence length? Yes, I can, by changing the exponent, the R alpha. So basically, by changing this RAB term, the repulsive term, I can tune and get a different, I can tune the persistence length. This is persistence length versus a tuning parameter. So I'm having a spherically symmetric potential by which I get linear semi-flexible chains with different persistence length. Of course, if I tune it, the branches also increases, so I don't want to be away. I want to be, if I want branches, as Raghunathan told me that for some studies he wants it, then I can also introduce branches. Something which has been strange that I went directly from the isotropic phase with small chain lengths to a hexagonal phase with long chain lengths, the first order transition, and the nematic phase was missing. The reason was I had long range repulsions between the particles which forced it into the nematic phase. So if I cut down, if I suitably adjust the potential so that the repulsion rises much more sharply than what was there in the previous case, this potential has also been cut down so that the repulsive at long distances rises much sharper. I do get the nematic phase. This is very new results. We are trying to do a systematics of it. And with that, I come to the end of my talk. My conclusion is, finally, after 20 years, I have managed to obtain self-assembled polymeric chains using specially designed spherically symmetric potential with tunable persistence length. Acknowledgements: this work was done by Alex Abraham, who was a 5th-year student in IISER Pune, and of course Rahul Pandit, and I thank you for your attention.
Questions?
So you get reasonably entangled, so macroscopically isotropic, entangled phases. So basically what I'm saying is isotropic phase, no order, but the persistence length long in, the connectivity is robust enough so that you get long chains,
yes.
But the chain...
You want branching? I have already...
I don't want branching. I want entanglement without branching. Can you get respectable amounts of entanglement without branching? Or is that your next... Yeah. All right, okay.
This entire potential has been designed to get entangled long chains, shear them. That is my aim.
Okay.
I needed the nematic phase. Now I'll...
Okay.
What prevents A being connected to two Bs?
Pardon?
In your model, you got A, B, etc.
A, B, yeah.
So what prevents A being connected to two Bs?
A being connected, I mean, it does get connected to two Bs if it is in a linear, I mean, A does get connected to two Bs on two sides. Like B is connected to two A's, each A is also connected. You want mean a triple one. There's a repulsion between AA's and BB's which has been tuned. So if the potential is, so between A and B, you have this minima and the repulsion. Between AA or BB, before this particle can approach, suppose another red particle also wants to approach, it will be repulsed away by the repulsion of this and this. So there is this extra repulsion term which has been tuned, which keeps, so here if there is a red particle, that would get repulsed by this and this, so it won't form.
Artificially somehow you have prevented branching.
Absolutely. And I can, if I want, I can tune it back and get branching. At high densities, I will anyway get branching.
No more questions. Let us thank the speaker once again.